The modern electrical grid is a continent-spanning metabolism. It functions on a constant physical requirement. Energy supply and demand must balance across every node at all times. Every generator physically tied to the North American interconnection must oscillate at exactly 60 Hz. If that frequency deviates, the machines risk tearing themselves loose. When a primary generator drops offline, the immediate shortfall forces the grid's frequency to sag. This triggers automatic load shedding, which pushes the electrical burden onto neighboring substations. As those substations exceed their thermal limits, they isolate themselves to prevent a total meltdown. In minutes, these islands of darkness expand across the entire regional interconnection. Behavioral models of extreme crises divide populations into a predictable 10-80-10 distribution. 10% of people will become hysterical, unable to process the loss of modern life. 80% will find themselves stunned by normalcy bias, waiting for an authority figure to issue instructions that will never arrive. Only the remaining 10% will rely on pre-programmed protocols to act decisively. Restoring a collapsed grid requires a black start sequence, a complex optimization problem that can take months. Modern power plants require electricity to operate their own internal pumps and control valves. They cannot simply be switched back on during a total blackout. The true timeline of survival is immediate. The first 24 hours are the golden window. This is the brief period where residual infrastructure temporarily hides the permanence of the collapse. Your mobile device will likely show a full signal even as the network dies. Cell towers rely on lead-acid or lithium-ion battery arrays that deplete within 2 to 8 hours. Even if the tower has power, the fiber optic backhaul, the physical lines connecting it to the broader internet, will lose power miles away. The tower becomes an isolated island, incapable of routing data or calls. As municipal pumps fail, the water pressure in the pipes will vanish. This creates a vacuum, allowing groundwater or untreated waste to backfeed into the residential plumbing. Harvesting clean water must happen before this contamination occurs. A standard water heater contains 40 to 80 gallons of potable water, but a hydraulic airlock will prevent it from flowing out of the bottom spigot. To bypass this, you must close the cold water inlet valve, then open the highest hot water faucet in the house. This breaks the internal vacuum, allowing gravity to pull the water through the lower drain and into your storage containers. Day 1 survival prioritizes the capture of geographic data, text coordination, and thermodynamic water reserves before the system's residual energy is spent. By the second day, the threat shifts to the sewer system. Without electricity, municipal lift stations fail. This causes raw sewage to back up through the underground network, pushing biological waste directly into the home environment. Standard plumbing becomes a hazard within 48 hours. Mixing liquid and solid human waste in a bucket creates an anaerobic slurry, a toxic breeding ground for pathogens like cholera and dysentery. The two-bucket protocol separates waste at the source to prevent this. Urine is collected, diluted, and safely dispersed on non-edible vegetation. Feces are kept in a separate, lined bucket and covered with a 1-to-1 ratio of dry carbon, such as sawdust or wood ash. This absorbs moisture and initiates a thermal composting effect, neutralizing pathogens before they can spread. On day 3, initial water reserves will likely run low. Since boiling water requires finite fuel, you must construct a biosand filter to process compromised surface water for long-term use. In a biosand filter, water passes through sand and gravel. Mechanical trapping sieves out larger pathogens, while adsorption captures smaller microbes deeper down. Atop the sand sits a 5-centimeter layer, the Schmutzdecke. Here, non-harmful microorganisms actively consume pathogenic bacteria, performing critical biological predation on incoming water. When civil infrastructure fails, the individual must engineer and manage their own microscopic biological ecosystems to remain hydrated. Day 4 often marks the need for scavenged electricity to power radios or medical gear. If you plug a portable generator directly into a wall outlet, you create a backfeed hazard. Power flows through your residential panel, back to the street, and into the municipal transformer. The transformer steps that voltage up to thousands of volts, creating a fatal electrocution risk for anyone working on the lines. Scavenging power safely involves deep-cycle automotive batteries and DC to AC inverters. This setup requires strict adherence to connection sequences. positive to positive first, then negative to a separate metal ground to avoid igniting vented hydrogen gas. To protect this hardware from a high-altitude electromagnetic pulse, you must use a nested Faraday cage. The outer conductive shell absorbs and grounds incoming waves, but as this exploded view shows, the internal device must be wrapped in non-conductive foam or cardboard. If the electronic device touches the metal walls, the protective shielding will instantly transfer the pulse into the circuit. By day 5, the psychological weight of isolation becomes a liability. Intelligence gathering requires a tactical communications network to track regional events. Signal propagation depends on the environment. VHF signals have long wavelengths that bend over rural hills, while UHF signals penetrate the concrete of dense cities. For encrypted off-grid communication, LoRa mesh networks allow devices to hop text packets across a decentralized web without needing any existing cellular backbone. On day 6, the risk of structural fire peaks as people resort to candles and improvised indoor heating. Without a fire department to respond, a single spark will result in the total loss of all stockpiled assets. Fire extinguishers degrade over time. Internal rubber seals eventually leak, causing the nitrogen propellant to dissipate. If the pressure gauge falls below 8 bar, the unit will not have the force to expel the chemical. Furthermore, the dry powder often compacts into a solid mass at the bottom of the cylinder, requiring you to physically invert and agitate the unit to keep it functional. Preserving the perimeter requires monitoring the mathematical and chemical degradation of your emergency tools before they are actually needed. 168 hours have passed. By now, the mechanical reserves of the old world, the fuel in the generator, the water in the tank, are nearing depletion. As the hardware of modern life fails, the struggle shifts to the human psyche. Constant threat assessment in an environment of total scarcity leads to chronic reflexivity. In this state, the brain is locked in a loop of recalculating every possible danger. This mental exhaustion destroys the capacity for interpersonal trust. Social erosion accelerates as community altruism is replaced by paranoia. Without a functioning grid to provide security, people begin to view every interaction as a potential threat. Intergenerational trust evaporates, leaving the population in a state of emotional isolation. The golden window has closed. The population that remained paralyzed while waiting for rescue has likely succumbed to dehydration or biological contamination. The temporary blackout is now a permanent reality. Those who survive this transition are those who replaced modern comfort with the active management of physics and biology. Survival follows the strict application of discipline and tactical knowledge. The grid is gone. The blackout is total. But the prepared mind remains.